My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 369. In this lecture, we will try to understand why L1 regularization creates sparsity. We made a comment saying that L1 regularization creates sparser solutions or creates sparsity, introduces sparsity in weight vector as compared to L2 regularizer. Why does L1 regularization creates sparsity as compared to L2 regularization? Just give a quick overview about sparsity means. Sparsity basically means here your W is basically a d-dimensional vector, that is W1, W2, so on WD. Sparse solution basically means that more components, that is more of your Wi's are equal to 0. Wi's means W1, W2, so on WD. I will repeat, sparse solution basically means more components of W are equal to 0 when you use L1 regularization over L2 regularization. We will try to understand why does L1 regularization creates sparsity over L2 regularization with the help of geometric intuition. What does it mean? How does your optimization problem looks like? Your optimization problem looks like this. Minimize W, you have a loss. This is about L2 regularization. In logistic regression, you have logistic loss. In linear regression, you have squared loss or OLS, ordinary least square loss. Along with it, you have L2 regularization with hyperparameter lambda. Just see here, this is L2 regularization. Of course, this is lambda is parameter, isn't it? That is minimization of W, loss plus lambda into this is L2 regularization. So, similarly, in L1 regularization, what do you have? You have loss plus minimization of W, loss plus lambda times L1 regularization, isn't it? This is lambda times, this is L1 regularization, this is L2 regularization, isn't it? Since loss is same in both the cases, if you compare this, just see, loss is same in both the cases. Since loss is same in both the cases, if you are solving logistic regression, loss in both cases is same. For the comparison between L1 and L2, loss remains same. Loss is constant. Let's just ignore the loss here. That's what I'm doing. That's what we are doing here, isn't it? Just see, this is loss is same. Loss remains same. You can neglect this loss because just see, loss remains same. Loss is constant. Let's just ignore the loss. Let's ignore the loss here because we are comparing lambda into this is L2 regularization plus lambda into L1 regularization, and loss does not make big impact in this case. Lambda is hyperparameter for logistic regression. Lambda is also a constant for this optimization, so we can ignore it. Therefore, you can also ignore lambda in both the cases. Now, what we left with? We are just left with minimization of W. What is this? This is L2 regularization. This is minimization of W. This is I can say this is L1 regularization, isn't it? Yes. Remember here, what is your W? W is d-dimensional vector, W1, W2, so on wd. In the place of w, I can write that d-dimensional vector w1, w2, so on. It is a d-dimensional vector. So its minimization of w means you are minimizing over all the components. What are the components? Minimization of, instead of w, let me write its components. If I write it, just see, I will get like this. In the place of w, I am writing as it is d-dimensional vector w1, w2, so on, wd, isn't it? What is this? This part is, this is what? L2 norm. This is L2 norm of w, isn't it? What about this? This one is L1 norm, isn't it? This is L1 norm. It is a vector, weight vector. If you observe carefully, just see this one. Here, just see w1. w1 does not occur with any other w's. Similarly, here also w1, here w1 occurs only here. Here it does not occur with any other wi's. Let's look at only from w1's perspective. Let us look at only from w1's perspective, isn't it? Because w1 is not being multiplied by anything else. So if you look at only from w1's perspective, this problem effectively is, how this problem will be? Minimization of what is this? w1. Here just I can write w1 square. Here what will I write? If I compare only with respect to w1 perspective, here I can write w1. This is absolute value of w1, isn't it? Now let's plot these two functions. Just let me, how can I plot? Just see, this is minimization of w1 square, that is L2 regularization, minimization of w1 with absolute value of w1. I can say minimization of w1 square means this is L2 regularization, this is L1 regularization, isn't it? Now let's plot these two functions. Which functions? w1 square and absolute value of w1. What is this w1 square? Here what happens? Just say this one. Let's call this is contribution of this. Let me take w1 on x-axis, L2 of w1, that is w1 whole square, isn't it? That is L2 regularization. Let's call this part as w1, and this is absolute value of w1, L1 of w1, isn't it? Now let's go and see how graphically it looks like. This is a graphical representation, isn't it? Minimization of w1 square, that is L2 regularization, w1 square with this is w1 square with respect to w1. w1 is on x-axis, w1 square is on y-axis, isn't it? My L2 of w1, I am taking L2 of w1 on y-axis, which is equal to w1 square. It looks like hyperbola, isn't it? This is I can say it's something like some it's look like it's a parabola, isn't it? Something like y square x square equal to 4y. Basically it's a parabola. L2 of w1 is w1 square, and w1 is on x-axis. Similarly, what about w1? L1 of w1, that is which is equal to absolute value of w1. How will you define mod x? Mod x equal to x if x greater than 0, minus x if x less than or equal 0. Therefore, what is this mod of w1? Absolute value of w1 is essentially w1 equal to mod w1 equal to w1 if w1 is greater than 0, minus w1 if w1 less than or equal 0. Graphically what it says, this is the graph of absolute value of w1, that is mod w1. To find minima, what we are solving, we are trying to solve minimum value. To find minimum value, we have to take derivative. Let me take derivative of first one. If I take derivative of first one, what happen? Dou L2 by dou w1. What is d by dx of x power n equal to n into x power n minus 1. This is 2w1, isn't it? w1 square means what? 2w1. What about this dou L1 by dou w1, which is equal to plus 1 if W1 greater than 0, isn't it? Which is equal to minus 1 if W1 less than or equal to 0. How derivative function, just this is derivative, how derivative function looks like. Derivative function, let us try to plot derivative function. Yes, let me plot the derivative function. Just see, this is our derivative. Which one is our derivative? This is L2, L2's derivative. This is L1, whose derivative is this W1 with respect to W1 1, that is plus 1, W1 with respect to W1 with minus 1. Therefore, dou L1 by dou W1 equal to plus 1 if W1 greater than 0, equal to minus 1 if W1 less than 0. Isn't it? Now we will try to plot these derivatives. How can I plot? Just see this one. Yes. Just see this plot. Okay. This one. What is this? Here you have dou W1 on x-axis, dou L2 by dou W1, that is 2W1. This is the graph of this one, isn't it? On the other hand, the derivative of L1 looks like this is W1 greater than 0. If W1 greater than 0, this is exactly 1. If W1 less than 0, it is exactly minus 1. If this is my W1, dou L by, if this is my W1, your dou L by dou W1 exactly equal to 1 if it is positive, and equal to minus 1 equal to if it is negative, if W1 less than 0, isn't it? This is how my function looks like. What is the update function looks like? Suppose I am finding my W1 at iteration 0. I am finding W1 at iteration 0, W1 at iteration 1, so on. I can say, let me say I am finding W1 at iteration k till the time it converges. That's what we do in gradient descent. So either for L1 regularization or L2 regularization, my W1 at iteration j plus 1 equal to my W1 at iteration j plus 1 is equal to at iteration j minus how just let me write otherwise. Yes, this is, let me repeat, W1 at j plus 1 equal to W1 at j minus R into R times dou L2 by dou W1 at W1j. This is about L2 regularization. Similarly, what about L1 regularization? W1 at j plus 1 equal to W1j minus R into dou L1 by, this is for L1 regularization, dou L1 by dou W1. Exactly same formula. The only difference is here I am writing L2. Here we are writing L2. Here I am writing L1, isn't it? And we have these W1j plus 1 as well as W1j plus 2. What is dou L2 by dou W1? If you write here, this one I can say W1 at j minus R times dou L2 by dou W1. Just go to the previous slide. Dou L2 by dou W1 is 2 into W1j, isn't it? In similar manner, here let me say if W1 is greater than 0, this will become 1, isn't it? Let me consider the case W1 greater than 0. What happens? Just see this one. Just see this one. This is the case. W1j positive. Positive means if it is greater than 0. Anyway, dou L2 by dou W1 is 2j. If W1 is greater than 0, just see this graph. Just see this graph. Let me consider W1 greater than 0 means what is this dou L1 by dou W1? This is 1. Therefore, in the place of dou L1 by dou W1, I am keeping 1 R into 1. But whereas here dou L2 by dou W1 is 2 into W1j, isn't it? What happens when you are trying to solve this problem? When you are trying to solve minima with L2 regularizer, as you are approaching your best value, isn't it? What is approaching best value means? This one. This is minimization means this one is optimal value, isn't it? This is optimal. As you are approaching best value is W1 star. This is this is W1 star. As you are approaching best value, that is W1 star, 1 star. In this case is also, this is W1 star, isn't it? This, what is happening as you are approaching W1 star, your slope is decreasing. Just see, your slope is decreasing, as you can see here, isn't it? Slope is decreasing. For example, W1 becomes very small. The best W1 star is 0. In this case, L1 regularization, in the case of L1 regularization, also W1 star equal to 0. Let's just say at jth iteration, the value of W1 is 0.05. Let me assume like this. Just say like this. Let me assume at jth iteration, W1j value is 0.05. So a very small value. Let's assume this value. Now what happens here? The slope is so small. Now the slope is small because your slope is small. Why? Because your W1j is equal to 0.05. Isn't it? This W1j is equal to 0.05 means it is just nearer to the minimum value, that is 0. Therefore, in this case, just now we are explaining. Just see this one. Just see, as W1 is 0.05 means just you are approaching to W1 star. Therefore, obviously the slope will decrease. Just see, your slope will, let's just say at jth iteration, the value of W1 is 0.05. So very small value, let's assume this value is 0.05. Now what happens here? The slope is so small. Now slope is small because W1j is 0.05. R is a constant. Let's assume R equal to 1. Let me say my R equal to 1. For simplicity in both the case, let's say R is small value. As your iteration number increases, R value reduces. Let R is also small value. Now here you have small value. What is this small value? 2 into W1j, isn't it? Now small value of R when we multiply, let me assume R is also small value. Why? Because R will reduce as number of iterations increases. Let me assume instead of R equal to 1, R is small value. If it is a case, what happens? When we multiply both the small values, I am assuming R is small value. Why? Because as iteration number increases, your R value decreases. That's what we discussed in learning parameter lecture, isn't it? Therefore, R is small value, W1j is also small value. When we multiply both the smallest values, what will you get? You will get a value which is greater than 0 but less than 1. When we multiply two small values, result becomes very small, isn't it? Yes, your result becomes very small. This is about your result become very small. Why? Because I am assuming this is small value, this is small value, isn't it? Now, what about in the case of L1 regularization? Just see, in the case of L1 regularization, what happens? Just see this one. Yes. In the case of L1 regularization, let me consider this term. Yes. Just let me take, this is R into 1. Here you have R into 2 into Wj, isn't it? R into 1. R into 1 means what? What is this one? This is constant. This is constant. So you left with small value instead of very small value. Here you have very small value. Here you have very small value. Why? Because R is small, W1j is small. If you multiply two small values, you will get very small value. Here you will have constant, let me say. Here you have only small value, not very small value, isn't it? Here in the case of L1, R into 1, this is constant. So you left with small value instead of very small value. Let R becomes, let me assume, let it be. Let R become 0.01. Let me assume my R equal to 0.01. Let it be. Otherwise, let me write here. Yes. Let R equal to 0.01. Isn't it? Let r become 0.01 because reduce r as number of iterations increases. That's what we discussed when we learning about learning rate changes with iteration number. If r is small, let me assume r equal 0.01, and also let me assume w1j is equal to, let me say, 0.05, small value, isn't it? Therefore, what is this r into what is my r? R is 0.01 into 2 into 0.05. You will get approximately, you will get 0.001 you will get, isn't it? On the other hand, what will you get here? Here you will get just r equal to 0.01. Here 0.001, here 0.01. Is it not? Yes. In L2 what happens? In L2 if I calculate, just see this one I assumed. Yes. In L2, W1j plus 1 equal to W1j minus R into 2 into W. I am assuming W1j equal 0.05 and R equal to, I am assuming this, just if I multiply this, just R into 1, this is small, but whereas R into 2 into W1j is very small. If I calculate this one, what will I get here? This in L2 regularization, my W1j plus 1 value, is equal to W1 at j. What we are assuming, W1 at j is 0.05 minus, what is this value? Just now we calculated R into dou L by dou W1, that is 0.001. You will get, what value you will get? You will get 0.049, isn't it? What about for L1 regularization? 0.05 minus 0.01, you will get approximately 0.04. Here you will get 0.049. In L2, as you come closer and closer, your derivative becomes 0. That's what I discussed, isn't it? On the other hand, here the derivative, just see, here the derivative in the case of L2 regularization, in L2, as you come closer and closer, closer and closer to your optimal solution, your derivative becomes 0. On the other hand, here just see here what's happening here, the derivative is constant. This derivative is constant. In the case of L1 regularization, the derivative is constant. The derivative is always constant. The derivative is always 1. Here the derivative is 1 if W1 is positive. But here in L2 regularization, as you coming closer to your optimal solution, closer and closer to your optimal, that is W1 star, derivative is reduces. So your rate of convergence is also decreasing here. The speed at which, simply I can say, here you are getting W1j plus 1 value. What is your W1j plus 1 value here? Here in the case of L2 regularization, W1j plus 1 is equal to 0.049. That is essentially W1j plus 1 means what? 0.05 minus 0.001, that is 0.049. For L1 regularization, what is your W1 j plus 1? That is equal to 0.04, isn't it? That's what we calculated, isn't it? In L2 regularization, as you are very close to 0.05, just see 0.049 is very close to 0.05, and keeping with if you continue these iterations, because of derivative is constant in L1, in L1 and derivative is decreasing in L2. Here your slope or derivative or gradient, your slope is decreasing, your slope is constant. If we keep doing this multiple times, very quickly we notice that L2 regularizer does not move much, isn't it? Does not change or does not move much. the value of W1 from one iteration to other iteration, from jth iteration to j plus 1th iteration. L1 regularization is, what is this L1 regularization? If you this derivative is constant, isn't it? In L1 regularization, this term dou L1 by dou W1 is constant, isn't it? The value of W1, if you move towards 0, isn't it? If W1 it moves towards towards 0, what is this derivative? This derivative is constant. This derivative is constant in L1, and gradient is decreasing in L2. In L2 regularization, it decreases, isn't it? In L2 regularization, just if you compare derivative, I think I must compare derivatives. In L2 regularization, isn't it? What happens? This dou L2 by dou W1 value is decreasing. Just see, it's decreasing. Here it is constant. I must compare derivatives, not this one. This is dou L2 by dou W1. This is dou L1 by dou W1. Dou L2 by dou W1, your gradient or slope is decreasing. Your derivative or gradient or slope is constant, isn't it? Sometimes people use gradient and slope interchangeably. I can say gradient equals slope. Since slope reduces as you are coming closer and closer to optimal value. Just see, this dou L2 by dou W1 is slope. It's what's happening. The slope is reducing. The slope reduces. As slope reduces as you are coming closer and closer to optimal value L2, your update is also become slower. Your update is slower. Your update is slower. Isn't slower. In the case of L1, the slope is constant. Dou L1 by dou W1 is constant, isn't it? The slope is constant. Much fewer iterations, your chance goes to this weight vector will become 0, isn't it? L1 creates, I can say, as it is constant, L1 creates sparsity. L1 creates sparsity. Just let me say, L1 regularization, just see this one, L1 creates sparsity because these two plots. Which two plots? L1 creates sparsity. L1 creates sparsity because of this plot, isn't it? As you are as this particular dou L1 by dou W1 is constant, here dou L2 by dou W1 is decreases. It does not create sparsity. That's what it says, isn't it? As you go towards optimum of W1, just see, L2 regularization does not change the value of W1 from one iteration to another iteration. In L1 regularization, continues to constantly reduce. This means what happens, this value of weight vectors becomes just 0. Just see, if you understand this entire concept, this entire thing will land with these two graphs only. Here dou L2 by dou W1, here dou L1 by dou W1. This is the crux, I can say. These two graphs are crux. This is a crux. This is the crux of idea, isn't it? Just go through this one. Just observe it carefully. If you observe it, what it says, what does it mean? In L1 regularization, chances that W1 equal to 0 are more at the end of kth iteration. That's important, isn't it? L1 regularization. Whereas in L2 regularization, less chances of W1 equal 0 at the end of kth iterations, isn't it? At the end of kth iteration, less chances to become 0. Why? Because just try to understand these two graphs. Just try to understand this graph and correlate these 2 points. What are those points? This is one point, this is another point, isn't it? In the case of L1 regularization, chances that W1 equals 0 are more at the end of k iterations, whereas in the case of L2 regularization, just less chances of W1 equals 0 at the end of k iterations because of these two particular graphs. This particular graph is related to dou L2 by dou W1. This is related to dou L1 by dou W1, isn't it? Just go through it. If you have any difficulty, please keep a comment. Thank you very much. This is simple geometric intrusion for why L1 regularization create sparsity. Thank you very much.